Thank you very much, Tim. I really appreciate the intro. This is my first SANS ICS conference, actually, so I'm a first timer in addition to a lot of you out there right now. And I just wanted to say before I started that this is a community that is fantastic. I actually got to meet Tim's mom last night in Disney World, and so it's a magical time to come here. Disney World's great. There you go, Rob. I'm going to give a plug there. It's a fantastic place, and it's a community that is welcoming, open, is adaptive, and fantastic. And if you are a first timer here along with me, I hope that this is going to be useful to you. And in that spirit, there is a spirit of collaboration. And that's what I'm here to talk about today, is collaborating with you. The lab complex, my sisters and brothers at INL, as well as NREL and the other 15 labs in the lab complex, have some tools that we want to help bring to bear to answer some of the biggest questions. That's why the lab complex exists for the DOE. We are able to take resources that might not be available to commercial entities and bring to bear on these massive problems, something that hopefully can solve and push our industry forward. So I'm going to show off a set of tools today that we use at the lab in order to do some modeling and simulation. And a use case for that is actually cloud. Most of the OT engineers, when I start talking about, and I will talk a little bit about control from the cloud, we won't dive too deeply into it. We'll talk a lot about data analysis. And in doing so, I'm going to show off a system called Phoenix and Mini Mega, which was actually developed at Sandia National Labs. And we've been able to build upon in order to answer questions of scale. I am no longer in the business of trying just to create a digital twin. You guys hear that a lot in our industry right now. And instead of digital twin, I want us to think about, especially when we start talking about the problems of the scale of this, of the renewable energy grid, right? These things that don't have inertia like we had in the past, the things that aren't these really, 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 really reliable diesel generators that have something that keeps spinning if you lose fuel, right? In order to answer these questions, we've got to start to scale things up from the bottom. And we have to be able to simulate things all the way from the distribution, the feeders, et cetera, all the way back up to generation, and then the cyber control systems on top of that. And then we can see a whole picture. We have to see this whole picture in order to answer some of these questions, and cloud plays a pretty important part in that. How many people do I have, and I'm going to try to see, from rural co-ops and municipalities out here? Okay, you guys are fantastic. You guys are running faster than the rest of the industry is in most cases, because you guys have one guy in your IT department that's trying to put out fires and run phones, et cetera, all the time. And cloud is here. And I'll tell a little story that backs that up. So in 2022, in the state of California, September 6th, if I recall correctly, it was the hottest day on record. And I think the peak megawatts production for the entire ISO there is about 52,000 megawatts. They were getting close, razor thin close to that peak. And once you start peaking, you have to start load shedding. And the way they handled this is the governor essentially just told people to turn their air conditioning off, right? Google came in with their Nest thermostats and were able to, I think the numbers are around 25 to 2,800 megawatts. And that sounds like a lot, but when you're talking about an ISO for the state of California, again, that's a razor thin margin. And they were able to pull that power back. They were able to basically keep the grid from actually going dark and starting some of those really dangerous rolling blackout operations. And so cloud is here. Cloud is already doing stuff years, plural, ago at this point. And so this is something that the government kind of freaked out about. What do we do? Let's go to the lab. Let's try to build an environment where we can actually start to look at what happens in bulk energy systems with cloud operation. And how do we answer, again, these questions? So Cloud Zero was born. We wanted to empower industry with data and actual data with a live cloud environment to essentially run some of these scenarios. And I know I'm going to try to get to some questions here too. I'm going to try to leave a little bit at the end there. So this is a multi-phase operation. Phase one was essentially making sure that we had a live cloud connection. We weren't simulating a cloud connection as has done in the past. And we were able to test latencies, et cetera, because you need real live connections in order to do this in the real world. We can simulate all day long, but we wanted something in commodity internet connected, commercial available cloud. So this is actually, none of this was done in GovCloud, just a side note. So phase one, we got the pipes running. Phase two, we created a much higher fidelity system. The complexity that we ramped up in phase two was exponential. And then future phases, we are, again, I'm here for collaboration. I want you guys to talk to me. My name is Anthony Wallace, anthony.wallace@nrel.gov. I'm looking for people to assist us in answering the next questions using this platform that we built, and I'll show and dive into some of the details that we found in phase two and how we can start to answer future phases of the grid, future versions of the grid that some cases we haven't even imagined yet. Just went through phase one. Some of the things that we came out with phase one was we had a worst case scenario for some of the connectivity that we did, because the way we set it up from a compliance standpoint is we actually had tunnels within tunnels to separate our network traffic from other network traffic. And so even in those worst case scenarios, we were seeing averages of 40 milliseconds for the cloud connectivity and for data to be transferred there. And so again, when I start talking about latency on the wire, OT engineers tend to squirm and they're like, well, you can't do anything with 40 milliseconds. I mean, there are laws of physics that we cannot overcome, and there are things that will always be on-prem. Governor control, exciter control inside of a generator, for example. That's not a cloud thing. We will never try to push it to the cloud. Again, speed of light is a limit. And so the larger operations that we see that are on the minute scale, the hour scale, those are perfectly within the realms of acceptance for some of these latencies that we're seeing as an outcome for phase one. And that cloud-provided tools are actually come a long way. We used Amazon Web Services in this particular instance. We have a great team called Stratus at NREL that actually sets all of, assists us with setting up research-based cloud services and not just enterprise cloud services, right? So we can actually start doing power systems research. And the cloud services offered by Amazon, I will say, are a bit more forward-thinking in some cases. So Azure is great, GCP is great. Amazon has an entire team of power systems engineers that have decades of experience in this region, and they've got services set up specifically for disaster recovery scenarios that we were able to test from phase one. These are published on our site as well if you're looking for phase one and then phase two, which I'll get to in a moment. So all of the basis for starting to answer higher fidelity questions in phase two. We had a great run with phase one. We got into a room with large operators like WAPA, et cetera, and some large players in the game and said, what keeps you guys up at night? We have a system, we want to test it, we want to build something out, and we want to show you guys how cloud connectivity might be able to help you or maybe hurt you. We are trying to be unbiased in this research. We're not going to shove cloud down anybody's throat that doesn't want cloud in their system. But what our team found is there's reliability to be gained in some services. And so we came up with 3 high-level goals for phase two. High availability and scaling, that's a pretty obvious one for cloud services. High fidelity load forecasting. The machine learning aspect of this, I'm going to say machine learning and try not to use AI buzzwords here, but machine learning aspects for things like time series data and load forecasting. And then BROS. Sorry, I hate that. BROS. Hey, bro. It's bulk electric system reliability operations. That's the one that starts to become a little bit contentious because we start talking about control, but we'll get there. So in the first phase, we spun up, I think it was like a 20-bus microgrid model, very small. NREL had an engagement with a military installation where we were doing resilience research that we were able to pull their data and model at a very low level some of their systems. And what we wanted was scale here. Scale's key. What cloud does is unlock the ability to process data in mass, in incredible mass, right? And so we needed something big. And so we created, using OpenDSS for the distribution system and PowerWorld for the transmission system, this purple region in Austin, Texas that you see here. And that's what this is, Austin. And we were able to we have a 5 terabyte data lake at NREL for load curves for the cities of San Francisco, Austin, and Atlanta. We picked Austin for some FERC 2222 reasons, actually, for future phases of Cloud Zero because of aggregators. And again, we'll also talk about that in a second. And we were able to model this purple region here, which has approximately, it's really more like 78,000 loads, commercial and residential in this area. And OpenDSS represented almost 30 substations throughout this distro. We had 2 fictitious distribution companies with a transmission company sitting on top of that. Again, we use PowerWorld for the transmission. Travis County, which is the county that Austin sits in for that particular model. And here's a picture of the visualization tool that we have that sits on top of this. Something that we found is super useful for your C-suite especially is being able to show the why, the whiz bang, right? You've got some people that Rob alluded to in a previous talk that like had never been in a substation that are in the C-suite, right? And being able to communicate to them the risk, being able to communicate to them in a clear way and method of impact when you start talking about cyber threat is key. And so this visualization tool that we've built on top of this is able to essentially take a model that we're pushing into our system and spin a visualization graphic on top of it. So this is Travis County transmission system, again, running in PowerWorld. And then you see the distro here. For those of you who aren't coming from an ICS background, red is good, actually. Red means you're dead. So red means the line is live. Green is bad. So green, you can touch it. If you walk into a SOC and you see a lot of green on the wall, that's actually not a good thing, right? So this is some of us actually trying to test out the blacking out parts of Austin, essentially. So you'll see that a lot of that is green, and this is just an image of that. By the way, all this data is open source. It's synthetic, so there are no coordinate type data that's associated with this, so that we didn't have to sign any NDAs with any particular providers or operators. And so you can actually use this data in your own models. We've got a zoomed in version here where you start to see the load level at the residential and commercial properties throughout. Again, most of it blacked out in some of our demonstration. And then on top of that, we have the cyber layer. So again, this modeling and simulation system that we use, Phoenix Mini Mega, and I've got links at the end of the slides here, allows us to, with a high fidelity, spin up representative infrastructure that is like corporate email servers, VPNs, jump boxes, things like that, that you would want inside of a scenario in order to create any type of scenario that we have cyber threat intelligence for. And I'll talk about how we spun some of that up too as well. This is really, really useful for, again, understanding this system of systems approach. And this is what NREL really try to dive into is how do all of these systems come together and affect change? And how does a person pivot from one machine to another? And something that is a little anemic here is this little cloud service provider you see up here at the top of the slide. That's what we wanted to build out in Cloud Zero and try to start talking about real workflows that are actually being pushed to the cloud from people who are even the smaller players like NRECA members, et cetera. And this is what we built in that little cloud. We tried to build it out a little bit here. Obviously, there's this portion to the left of the slides simplified greatly. We really want to focus on these pipelines that we were able to create for load forecast. So this is a short-term load forecast pipeline that does a rolling 12-hour load forecast in front of our simulation. And these were live services launched again in commercial available AWS, not GovCloud. We have an IoT core system, a bunch of other services that take the time series data via MQTT and move that through this pipeline and are able to generate an actual rolling forecast for that massive distro system that we were just looking at. I will say that when we set this up, we were not securing it intentionally. We wanted to make sure that we had just kind of a baseline. There are services that are discussed in our phase 2 report that will prevent some of the attack that I'm about to talk about from happening inside of these cloud environments. So this particular deployment is actually a multi-regional deployment that also was for our failover scenario, right? We wanted to see how fast we could flip over to our other region. In this case, if we had a failure in one region. And there are some requirements, NERC and FERC requirements that require space to be between some of your disaster recovery zones, right? So large spaces, like 1,000 miles at least. So these were set up on opposite ends of the country, basically. This was the output from that. So what we were able to produce, and this is something that I'll also say, I am not a machine learning engineer by trade. I am a lay machine learning person. But I can even come in here and set up a load forecasting system from our time series data that is fairly accurate. What you see in the middle here, this red line that's in the center, is the actual live replayed data. And then these regions out here are this range inside of the forecast. This is a 6-hour forecast, I believe. And so the machine learning services for services like Amazon Forecast have been set up by this team of power systems engineers to solve this problem. This is a very common set of services that a lot of you utilities do. We want to see what power usage is going to do over the next 12, 24, 48 hours. And these services can be set up without any hyperparameter tuning. So this particular model was actually generated without touching hyperparameters inside of, like, using SageMaker, for example, which is another Amazon service that allows you to create these models. So right out of the box, this is actually pretty useful. Setting it up securely is key, but again, reliability can be solved here in some cases for your data analysis services. If you're a lot of people do this on-prem. A lot of people have test beds that they're running these things in. A lot of people have ADMS systems that they're doing some of this forecasting in. Like, these forecasting services are actually pretty well what we saw right out of the box. Another thing that we tested was the capacity for that IoT service that you saw on this previous slide here. So how many things can we hook up to it? How quickly can we as a lab spin up those things so that we can answer some of these scale questions? Part of the Phoenix suite of tools that we have, we created an application we just call the AMI app right now. Advanced metering infrastructure is something that people are really starting to talk about in the industry nowadays. And we have the ability to spin up approximately 80,000 to 100,000 things or meters at a residential or commercial property in about 8 minutes. And so one of the things that we really want to bring as a lab to these, and our lab complex entirely wants to bring to cybersecurity, is a sense of rigor to these things that we're trying to build and these questions we're trying to answer. What happens when we change an independent variable in these systems? Well, it's very difficult at this scale to change an independent variable and then go back and shut everything down. And so what this orchestration system allows us to do is set an initial point, set an independent variable, test it, reset the system. We can literally hit a power button. I'll show you here in a second. I've got a video of it that allows us to reset to an initial state, change the variable, run again, right? Scientific method. So, and we can do this in mass, and we can do this very quickly. So this is, and I'm going to talk through this. This is about a 4-minute video. I might skip to the end a little bit or try to. So this is our Phoenix system. This is what you would deploy. Just it's the GUI. I apologize in advance for that. It's not great, but it allows us to see a system as a whole. These are your virtual machines inside of the system that are running, and those systems are the co-simulation systems that actually run the power model, and also those corporate systems that you saw in the previous slide where we talk about architecture that's actually being spun up inside of these fictitious corporate companies running these models. So from start to finish, from the stop point where you saw that it was stopped to a start point, again, it takes about 8 minutes to boot up. So we'll see it actually come online here in just a second. And then as it comes online, these are literally 81 virtual machines that are booting, just like they would in any other hypervisor. And the system helps orchestrate that booting process. We have scripts that are running on the virtual machines that do things, but there's also a Scorch. You'll see a tab at the top there called Scorch, which is a portmanteau of scenario and orchestration, Scorch, that allows us to start doing a threat intelligence scenarios running through these systems in mass. And so each of these virtual machines, and I'm going to try not to dive too deeply into the technical details here. I'll try to keep it a little high level, but each of these virtual machines has a back-end agent running on them that allows us to do that orchestration running via sockets. So you actually don't see the agent orchestration traffic on the network, which is a really fantastic thing because you're not polluting your data when you're trying to pull data out of these experimental environments. And so You can click into any of these machines like you would a normal machine. This is our Power World system that we're running our transmission on. It'll boot up here in a second. And then on top of that is our visual representation of the system that is going to be showing for basically pictures. This is a live video of the pictures that you were seeing of our system a while ago. As you're running through it, you'll see that all of these are separated, and like you can have some network segments like it's all VLANs together. And you can actually start a packet capture on any one of these machines just by clicking on it in the graphic user interface. You can go into a system and type on it just like you would any other system. The beauty of this system is mission rehearsal is really great in this particular environment. So we'll run an attack here in just a second, and you can actually have your operators go into the virtual machine and pull artifacts like they would off of any other machine inside of an exercise that you're running. Here's our Travis County system running in our Power World. The compute here, and I'm trying to remember, I can get you the compute statistics for the node that we were running on for this. This is a 1-node system. We have a 200-node system at NREL that we were about to instantiate that will allow us probably, I'm hoping, not just to run this urban area of Austin, but the entire city of Austin, and then maybe potentially even other cities that we can interconnect. So again, we're talking about scaling up here. We need to answer these questions at large scale. All of these systems have high fidelity DNP traffic flowing behind them. They have other, like we can simulate Modbus. We've got modules for other different types of protocols there. S7 is a module that we have in development right now. Sorry, S7 COM. So I'm just gonna, it's a long video, but I think I've hit most of the salient points. If you guys want, this will be available on the slide deck. It's 5 minutes and it's high res of my machine. So it made the PowerPoint presentation about 200 megabytes. So I apologize in advance for that. I want to make a comment about the co-simulation system behind it. So we use Helix. That stands for, and you see the transmission systems come online here. This is a live viz of everything that's running as the virtual machines in the model. Helix stands for Hierarchical Engine of Large Infrastructure ICS. Yes, control system or co-simulation. Thank you. So the Helix system actually allows us to tie together the transmission and distro in a way that would be like a live system. We actually have points of common coupling for your utility guys in here between the distro and the transmission. So if you poke the distro, meaning like if you shut down or open a breaker inside of a substation, you will see that reflected inside of the transmission via Power World. This is all cobbled together with some Python scripts. We're trying to improve efficiency there. But for right now, it's minimum viable product, allows us to answer some experimental questions. This is a particular video where we actually see, again, on that same simulation that you were just seeing, the back-end code for what's going to be going on to IoT core. And so if you click over here, we actually have live power data flowing from our environment, active and reactive power values flowing into IoT core via MQTT. So we took this system, as mentioned previously, we have a project called ETAC, the Energy Threat Analysis Center at NREL. It is a partnership between INLs involved in that partnership, other PNNL, ORNL, and we have 3 utilities actually currently in the pilot phase, which should wrap up here in the next couple of months, that allow us to kind of have a finger on the pulse of what's happening in threat intelligence inside of the utility industry directly. So we're shoulder to shoulder with people who have access directly to their SOC, and they can feed us data. And we can take that data and we can create really high fidelity and realistic threat scenarios that we can run through these environments that look like a representative system. We created 2 classes of attack in phase 2 for Cloud Zero. One class is a data poisoning attack, which I'll talk about here, and then another class was a control attack. The data poisoning attack is really fascinating, right? And I'll talk a little bit about some of the mitigations again against this. This is not something that I'm not going to come out here and say Amazon's inherently insecure. It is really up to the operator what security they're pushing into these systems, right? So we'll talk about some services to help prevent some of these attacks. The data poisoning attack is really fascinating because if you start changing if you were able to pivot to a point inside of this pipeline and change the values just a little bit, nobody's noticing, right? Eventually, you start getting up to levels if you're increasing these values to points where you actually have to take load shedding operation, right? And so that's, or the opposite direction, where you actually are not underreporting what you're actually having inside of your system. So we tried this class of attack, and we also tried this control class of attack. So we have a system at in RHEL, again, developed on previous systems that were developed at Sandia, called OTSIM, Operational Technology Simulator. This is a modular system that literally is architected to operate like a PLC. So there's a pub sub backplane that you can actually write modules for. You can write them in Python, C++, and those modules are either communication modules or modules that interact with the Helix system to allow us to affect change in the power model. And what we've done is able to create a virtual RTU that we deployed into the cloud on an EC2 instance that was wedded to a system that was down inside of our environment that controlled transmission breakers inside the transmission system. I can get into some of the very detailed points of this attack, but it's very basic. I mean, we really started with default credentials on an open box that wasn't protected by access control inside of a VPC, virtual private cloud at Amazon. So again, controls can be put in place, but we were creating some kind of baseline to start to work with. And then what we got was a system that has some vulnerabilities in it. An attacker has managed to breach that RTU in the cloud, and we deploy multiple frameworks. We've got Metasploit inside of our environment. We've got Cobalt Strike. We've got et cetera. But this was Caldera's MITRE's tool that we used to automate and deploy this particular attack. Live systems running live attacks on these power systems, and again, all the artifacts get stored inside of this system that you can pull out. You can show your incident response teams what these things look like. You can show your power systems teams what happens when a particular portion of your system is breached and a change is affected inside of that. So what you'll see here is that point of common coupling becoming disconnected, that transmission shutting down and going green. And because, again, it's a live system, you'll see it actually cascade throughout the rest of that particular distro system in this portion of Austin, Texas. So, potential mitigations. The Internet of Things core, the thing that's being fed this MQTT data, we used a single certificate for all 90. We were at the feeder level for this particular set of meters. All 90 of them had the same certificate. Obviously, that's kind of a bad practice. So making sure that you have certificate variability there, like you're actually deploying each, and there are tools to help you deploy that in mass. So like the 77,000 things that we deployed, it may take you a little bit longer, but trust me, certificates are always a good thing. CloudTrail, log everything in your cloud, and then have GuardDuty on top of that, working alongside it, that you can actually see some of these anomalies that are coming in. Have bounds that your data is expected to have coming in when you're doing your load forecasting, for example. Primary conclusions out of the box, some of these services provided by Amazon are actually pretty fantastic at doing their job. We have successfully showed that there's all the failover statistics are in the phase 2 report, which I'll have a link here at the end. It's a 40-pager, and we're really proud of it. I want to thank my team at NREL that helped us produce this over last year. It was about a good year of work that went into this. The co-simulation framework is able to answer some of these questions at scale. Again, I'm not in the digital twin business anymore. I want to build something up that is high enough fidelity, a general reference architecture, that I want to talk to utilities here in the room. I want you guys to look at and vet this general reference architecture to say, yes, this actually looks like a portion of my system. It is not an identical twin, but I can take that and use it in my system when we're doing these engagements and answering these questions. So I have about 5 minutes. I'm right on. I'll take questions from the audience, and thank you very much.